This week, we'll be taking a look at the ideal gas law. This is a extremely useful gas law overall that allows us to link our gas constants, our volume, pressure, etc., all the way into what eventually will be stoichiometry. The formula for the ideal gas law is pressure times volume equals nRT. A lot of variables on here, and one of the most important things to realize about the ideal gas law is that the gas is not changing. Unlike the previous ones, we had a gas being compressed or heated up. Here, the gas is at a constant. The pressure is not changing, the volume is not changing, the temperature is not changing. So P stands for pressure, and it can be any pressure that we've used so far, from atmosphere to torr, millimeters of mercury, or kilopascals. This time around, though, while V stands for volume, it must be in liters. This is primarily due to the R value that we're going to see later on. The R value is a gas constant, and we'll talk about that guy a little bit later on. He deserves special consideration. Then we have a new variable to look at, and that is N, number of moles. When we discuss number of moles in stoichiometry, this isn't entirely unfamiliar to us, but this is an important variable because it will link it to stoichiometry in the future. A truly brand new variable is the gas constant. Gas constant is kind of like a band-aid. We don't know everything there is to know about the gases and the behavior of the gases. Essentially, this is a number that simply works. It makes the formula work. We're not 100% sure why. Then there's temperature, and we already know that has to be in Kelvin. So as a final reminder before we take a look at that new variable, gas constant, this formula is not how a gas changes. It's how it is currently. It's actually very easy to measure the pressure of the gas, or the volume of the gas, or even the temperature of a gas. These are things that we can use pretty easily. We can use those variables to calculate the number of moles, which could then be used to convert to the number of grams. That we can't measure easily. We really can't put a gas on a scale. Or if we use stoichiometry and we calculate how much of a product is being made, in other words, how many grams are being made, then we can predict how much space it will occupy or how much pressure it will exert. We would have used these concepts had we been in class to do our airbag lab, where I would have had you fill up an airbag perfectly with a CO2 gas produced from hydrochloric acid and baking soda. And this is the one where I gave you a mild threat during the beginning of the year. And by this time, you would be able to do all your math and get it done within 2 tries without failing. Unfortunately, we can't do that now. Now let's take a look at that R value. The gas constant R has several numbers associated with it, and it all depends on what unit you use for your pressure. So, for example, if you use atmospheres as your pressure, then the R value you must use in your formulas is 0.08206. If you use a Pascal or a kilopascal, you will be using 8.314. If you use a torr or a millimeter of mercury, you'll be using 62.36 as the R value. Currently, we're not going to worry about the other tools where we have joules, which stands for energy, as well as a calorie for energy just yet. We wait for thermochemistry before we introduce those. So once again, depending on what atmosphere, kilopascal, or torr you end up using, will tell you what R value you must use for your formulas. If you use atmospheres, it's 0.08206. If you use a Pascal or a kilopascal, it's 8.314. If you use a torr or millimeter of mercury, it's 62.36. We will end our brief discussion of the ideal gas law talking about the number of moles. This variable is extremely powerful. Of course, it links us to stoichiometry and we could find actual amounts, but we can also identify gases from it. The formula that's hidden within it is N equals mass divided by molar mass. If you plug this into the formula, you end up with PV equals mass divided by molar mass RT. This means you could predict how much the gas actually masses out. Or if you know what the mass is, you can predict what the gas actually is by molar mass. Molar mass can often be used to identify what a chemical is. This is why the ideal gas law becomes very powerful in not only its link to stoichiometry, but also in identifying unknowns. This week, your homework will be on the ideal gas law, and we have about 10 problems to work with. In your assignment this week, we have the formula, which is PV equals nRT, and we'll be using two of the R values, the one that involves kilopascals, so 8.31, and the one that involves atmospheres, 0.082. These have been rounded a tiny bit. These are not the exact R values, but they're acceptable for this exercise this week. Let's take a look at number one. In number one, we're asked to calculate the volume of 3 moles of a gas that will occupy 24 degrees Celsius at 101.3 kilopascals. I like to list my variables when I first get started with this. I know that I'm going to have a pressure, a volume, the number of moles, some R value, and a temperature. Let's try to identify what we can here. Currently, it looks like our pressure happens to be 101.3 kilopascals. The volume, we don't know. It says calculate the volume. We can leave that as an unknown. N stands for number of moles. This is new to us. This is 3 moles. The R value, well, the R value is going to vary. Because we're using kilopascals as our pressure, we're going to use the kilopascal R value that's given to us in this exercise, 8.31. The temperature is 24 degrees Celsius. By now we know we can't use 24 degrees Celsius. We can convert that to Kelvin, which ends up being 297 Kelvin. So, solving for volume, PV equals nRT. I like to rearrange my equation before I plug in variables. We're going to solve for volume, V, which means both sides need to divide it by pressure. That means volume is nRT over pressure. Now I can plug in my variables. N is 3. The R value we decided on was 8.31. T is temperature, or 297 Kelvin. And the pressure was 101.3 kilopascals. Solving for this whole thing, you end up with a volume of 73.09. Then we need to discuss a unit. Because this is the ideal gas law, the volume must always be in liters, and that is primarily because the R value is always given in liters. I'm going to work on problem number 2 next. I have everything set up. I know I'm going to be working with the ideal gas law, so I wrote down PV equals nRT. I have my variables listed here. Let's take a look at number 2. How many moles of a gas would be present in a gas trapped within a 100 milliliter vessel at 25 degrees C at a pressure of 2.5 atmospheres? Looking at this problem here, I can identify pressure first. Looking through this, it looks like my pressure is 2.5 atmospheres. Volume, I scan through here, I see 100 milliliters. If I write down 100 milliliters, I must remember that in the ideal gas law, my volume must always be liters. Converting this to liters results in 0.1 liters. Remember, it's 1,000 milliliters to 1 liter, so I would divide this by 1,000. N stands for number of moles, and according to this problem, I'm looking to solve for that, so I don't know what this is. The R value, I'm going to have to choose. This is based off of my pressure. My pressure is atmospheres, so my R value will be the one that's given to me in atmospheres, 0.082. I will remind you that this is rounded heavily for this exercise. The actual R value is far more precise. It is 0.08206. T is Kelvin. We are currently given Celsius. That's a quick conversion. We know we add 273 to it, which results in 298 Kelvin. With all my units identified, I can now plug in and solve. Remember, we're solving for a number of moles here. Using the ideal gas law, PV equals nRT, I'm going to rearrange the equation for N first. In order to do that, I have to get rid of the variables R and T. So I'll divide by R and T, which will cancel them out. What I do to one side, I must do to the other. The end result is N equals pressure times volume divided by RT. Now let's plug in some variables. Here, my pressure is 2.5 atmospheres. My volume in liters is zero point 0.1. My R value, because it's atmospheres, is 0.082. And my temperature in Kelvin is 298. Make sure you use order of operations. This is a common mistake among the ideal gas law. It is still the product of the top divided by product of the bottom. So I'm going to make sure I do 2.5 times 1 first, and then divide it by 0.082 times 298. If you plug this into a calculator and you do this correctly, you'll end up with N, the number of moles, equaling about 0.01 moles of this gas. The last problem I want to work with you guys as an example happens to be number 8. This is still the ideal gas law, so I have the formula and my variable set up. In number 8, we see that a sample of argon gas at STP occupies 56.2 liters. Determine the moles of argon and the mass in the sample. And we have a few things to work on here. Not just do we have to find the number of moles, but we must also find the mass that this sample occupies. We also see a set of conditions known as STP. So this is a good refresher for what that stands for. Let's plug in what we know. I'm supposed to find pressure first. Well, pressure comes from STP. If we recall, STP stands for standard temperature and pressure. That is the same thing as saying 1 atmosphere, or anything equal to 1 atmosphere, the torr, the millimeter mercury, and so forth. But also 0 degrees Celsius. That's also the standard pressure and temperature. So we know here that our pressure is going to be 1 atmosphere. For volume, I scan through here and I see it is 56.2 liters. Thankfully, it's already in liters, so no conversions are necessary. And we don't know. It literally says determine the number of moles. The R value I'm going to choose based off of atmospheres. For this exercise, the R value is given to us at the beginning to use a 0.082. And then the temperature needs to be 0 degrees Celsius, but we know that to be Kelvin as 273 Kelvin. With all my variables identified, I can now solve for at least the first part of the problem, which is determine the number of moles. Using my ideal gas formula, PV equals nRT, I solve for N. Divide both sides by RT to get the number of moles by itself. N equals pressure, volume, times RT. Plug in the variables that we know. Pressure is 1 atmosphere. Volume is 56.2. The R value is 0.082. And the temperature was 273 Kelvin. When you solve for N here, the first answer for this problem is around 2.51 moles of argon. But remember, this problem also wanted us to solve for the mass of the sample. Now this is where we recall what number of moles is equal to. If you remember, mole is simply the mass of whatever element or compound divided by its molar mass or molecular weight. So currently we know the number of moles, we know N. We should know the molar mass because it's argon. Solving for this, I can solve for mass itself. If I rearrange my equation to solve for mass, I multiply both sides by molar mass, so I will end up with molar mass times the number of moles equals the mass. And so for this problem, I simply look up the molar mass of argon on the periodic table. The molar mass of argon is around 40. The number of moles of argon is 2.51. When I multiply these two together over here, I end up with 100.4 grams of argon. That's my final answer. Now I know how much this gas happens to weigh without ever actually putting it to a scale.